Hello, good morning, all. Hi, everyone. I hope you're doing well. Um, and good morning to everyone. Hi, good morning, Patricia. It's really good to always be here with you guys. Um, sometimes saying good morning to you guys are like the first words I speak out loud to anyone. So, hi, good morning, Mamet. Good morning, Gary. I see you too. Hi, Robin. Yeah, so I'm glad you guys are here. Good morning, Jonathan. I see your thumbs up too. Um, we have a good day ahead of us. Good morning, Bradley. Yeah, oh gosh. I'm trying really hard to figure out this internet issue. So if you guys, oh gosh, I think I'm on the wrong network. Good morning, Keon. Yeah, if you guys hear me cutting out or anything like that, you let me know, and we'll see how it goes. This is like spot number four in this room that I'm trying to figure out, see what works. It doesn't make sense to me. My router's in the same room that I'm in, but yesterday in the corner it didn't work, but now I'm like 3 feet from it. So I don't know. We'll see. I had a lot of internet issues last night. So yeah. I do have Spectrum, Owen. Is there a moment, something happening? I had that happen in the summer when I first moved to this apartment. Literally the day I moved in, everyone in downtown did not have Spectrum. So the one and only time I had to cancel class. Yeah. Ah, okay. You always had problems with them. Dang. Well, I don't know. I have to figure it out. But yeah, if anything happens, y'all let me know. I'm on my 5G network, and I think I'm supposed to be on the 2G. So we'll see. Yeah, we'll see. Everything else is on 2G. So I don't know. Yeah. Well, what day is it today? Tuesday? Tuesday? Yes, I am right next to it, and you're right. 5G is supposed to work on shorter range. So if you're closer, you should get more speed. But I also don't like the location of my desk here, so we'll see. I'm gonna just keep working on it. Maybe by spring semester, I'll get it going. Yeah. So today is Tuesday. We're completely on schedule for our lecture. That's nice, and we will have a lab today. I think lecture will end early too, and then we'll just move right into the lab. And again, both of those are my favorite of the whole semester, so I hope you have fun with it too. Um, any comments, questions, any concerns, anything in general from anyone? Good morning, Daniela. In case anyone is typing, I'll wait. Today we have the world's most diluted coffee. So just to keep my fingers warm, but it was a cup of coffee from this morning, and I've poured hot water into it twice already. So it's still going, but it'll keep me warm.
Oh,
Um, Hello, who's that?
would it still be possible for me to turn in the lab from Monday? I almost completed it last night, but
You
yeah.
know what, Gary? Go ahead and turn it in. If the link is closed, email me and I'll open them. But you guys can always submit late work. Um, it's good for you to check, you know. But it is in the assignment uh, description that you can always turn in late stuff. I
Okay.
really, yeah, I
I was a
really
little
care.
unsure because the new unit started, so I just thought I would ask first.
Yeah, fair enough to ask. Um, I can't help it. I'm a little bit of a softie when it comes to like late stuff. As long as you do it, I'm pretty happy, you know.
Thank you.
But I gotta tell y'all, I'm I'm in physics 101 right now, so this should be like maybe the first or second course if you were just starting college. Now I know we're all different backgrounds, so maybe this is like your fifth semester or something, but along the line you really gotta stick to those deadlines eventually, because some people they're gonna try to teach you a lesson about deadlines. I agree with deadlines. Some deadlines are hard, but I'm okay with you turning on some stuff late. Okay, let me just go through the chat and then we'll get started. I'm just kind of waiting around for a few people, for more people to come in. That's it. Um, Saja, yes, my diluted coffee for me is good. Seeing as I haven't had coffee in like 3 weeks, it's delicious. Oh, Keon, yeah, it's so cold. Yeah, you're right. You know, my heater just stopped working, so I have a space heater and yeah, that's why I'm wearing like this longer sleeve stuff because I need my space heater too. Um,
Opening the windows.
what?
People in my house keep opening the windows.
Keep them near the windows.
We keep opening the windows.
Oh,
Yeah, it's so cold.
wow. It is so cold, and it made me think yesterday. So I actually stepped out of my apartment yesterday, which is I don't often, and it was so windy, and it made me think of those of you last week who were really experiencing the wind so high, but I couldn't tell, right? I knew they were high winds, but yeah, yesterday that was intense. Oh, Daniela says, so yes, stay warm, guys, however you can. My mom likes to wear like 3 sweaters, a beanie, like 2 socks, and I don't. I prefer the heater. Daniela says my dad calls that agua de calcetines or sock water, diluted coffee. That's correct. I think that's right, Daniela. But for I haven't had it in a few weeks, so I'm pretty happy. Good morning, Nathan. Welcome
Have you
in.
ever
Oh,
tried
and
decaf?
say that again, Randy.
Have you ever tried decaf?
I haven't, but a really
This
close
has some
friend of
caffeine
mine.
in it.
Yeah,
Just a
I think it does have a little bit decaf too. I used to be very insulted by the word decaf, like
yeah, same.
decaf
I was like,
coffee.
why would you drink it? What's that for?
Yeah, I thought so too, but my close friend that also has experienced vertigo really bad, really intensely, like more so than I did. She recommended for me to have decaf too. And she said it'll only last a few months and then you'll be back at it. Oh, but yeah, I don't know about this decaf, but it's worth a shot. Anything to keep my vision and my mind going. So oh, and Saja says it was freezing last night. I was under 4 blankets. Yeah. Oh gosh, your cat, Keon. Yeah, that's tough. Yeah. I have 2 friends. They're real husky guys, and every time we're in cars, it could be freezing like 2 a.m., 1 a.m., midnight. But these 2 guys insist on having the windows wide open. And I'm like, I don't know. Um, Man, and yeah, real caffeine does hit differently. Even the smell of it. And then the last thing I'll comment on, and then I promise we'll get started. Nate says, I just got an espresso machine, and if you're a coffee junkie, decaf is great. Um, I'm going to start looking for an espresso machine because all I need is my one little espresso shot. I don't need much else. So I am going to look for one. I had been putting it off for many years. I kept thinking, no, I don't need it, but yeah, I think I do want one. Oh, all right. Target has some good ones. Breville's. Oh, thank you guys. Yeah, yeah. Yeah, I'm thinking of going that route, Nate, because I also want to avoid the expense. So I'm thinking of going Goodwill or OfferUp. My mom's really into OfferUp. So, or Nespresso's. Yeah, I'm thinking too. Yeah. We'll get there. I don't know if by next week, but if you guys are in Physics 102, I will update you on the espresso journey. Um, yeah, anything to wake up this morning, right? Well, I think our diluted coffee is it's gonna work this morning. Oh, you guys, Owen brings up a good point. I promise this will be the last thing. Speaking of Physics 102, do you know what the summer's looking like? So, for sure, there will be Physics 102 in the summer, but,
103 too?
huh?
103 also?
Not I don't think 103. If there is a 103, it'll be probably with Dr. Moreno, but I don't think there will be because he that's normally not his summer schedule. Physics 102, I will teach it this summer, and normally I teach it the first session, but I think I'm going to teach it the second session this year. So maybe that'll leave room for you to do something else the first session, but 100% there will be Physics 102 this summer for those of you that can't take it in spring and would and want to, or the if summer just works better for you. Yeah. Yeah, we'll have a lot of a little bit more free time next week, and so we can go into detail for like everyone's individual situation next week too. So we'll talk about this again. Okay, and then some nice cleaning tips about the espresso machine. Thanks y'all, because I'm very big on keeping things super clean. Okay. Um, well, y'all, I think our chat is even if I don't have caffeine, maybe just talking about caffeine is.
Drugs, actually, it's the same for drugs. Like people that talk about alcohol, they like feel the effects of alcohol before they take them. Just like if you hold the glass of alcohol, you act differently as though you were drinking alcohol. It's like scientifically proven.
Randy, I believe it. I
Food.
really do.
It's like
Yeah,
from a food, you feel hungry, you start watering, you know?
I really believe it. Or what another study showed that just the smell of coffee helps too.
Yep.
I love it.
Because it like triggers the same patterns of like releases of like neurotransmitters as because like like the experiment with the bell and the dog and the mouth watering. So like the smell
Yeah,
of coffee is the same thing. Like you experience the sensation of drinking the coffee before you have the coffee because you know that the coffee's coming because you usually smell that smell and then the coffee comes.
yeah, yeah. That's exactly it. Nate says to like dopamine.
Yep.
my 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 PhD advisor, I swear I'm starting the screen too. My PhD advisor one time, he needed us to stay overnight to watch an instrument because we were going to heat it really high and it needed to heat at a constant rate. So every few hours we needed to check it. And so me and another grad student were going to stay overnight. And this was kind of common practice in our lab and in other labs that had these high vacuum chambers. So he needed us to stay overnight, and she was a second year and I was in my first quarter. So he took us to the Coffee Bean on campus, and he was like, oh, order whatever you'd like, and then we ordered drinks, and this was like 5 p.m. And then he sat us down and he told us about staying overnight and all of that. And then he laughed at us and he said, I just doped you guys with caffeine. So he thought it was funny that he was doping us with caffeine to keep us up. It was all a sham under the guise of guiding us about what to do that night. He was really doping us. um, yeah, that might make more. Yeah, he was drugging his students, but it would make more sense if you ever take materials of engineering and learning about doping materials to change the effect of it. Yeah. Okay. Yeah. Yeah. Um, what? Oh, yeah. I think I heard that. It is the material.
I said you were the material, and
Yes, that's right. I, I thought I heard you right. Yeah, drugging the students, doping us. Okay, guys, I've shared my screen, and I think we have. Wow. Um, Randy, it's a little bit harder to hear you today. Maybe a different background. Just yeah. Hmm. Yeah, just a little bit harder, not too much, but maybe the volume or something. Um, okay, so I've opened all my screens. I still see all of you and your boxes. I see the chat screen. And now we're at 24 and we were at 16 earlier. So good morning conversation to get everyone in. Okay, so today we're going to finish off chapter 10 and everything that has to do with torque. And then we're going to go into the lab for torque, and I'll show you some tips and tricks of how to solve for it and make the lab easier and less frustrating, but it's still fun. After I read so many of your experiences with the acceleration lab, the goal, the that lab, yeah, I'll give you some tips so that it's not as frustrating. But you know, troubleshooting is part of the process. Um, and so this second section will get us into our next set of equations. So let's kind of I put it on this screen because this is a nice review of what we did yesterday and really a nice summary of the beginning half of the angular equations. So everything we've done so far is taking us from looking at tangential or linear motion and now looking at angular motion for rigid objects, rigid bodies. And again, a rigid body is something that is moving with it. We assume that it has a continuous mass, so it moves and rotates in the same way, kind of like a merry-go-round that's spinning, right? Everything on it moves together, and we assume that mass to be evenly distributed. So usually that's what you're going to work with. And this is because we haven't talked about center of mass, and I don't think we'll have time to go into it, but if you continue on to engineering and take statics, you will go into center of mass. And I think center of mass is very intuitive, so it'll be good. Okay, so what we did yesterday was come up with new, well, things we've kind of seen, but we came up with how to go from our linear world to our angular world. And we said that the position x now becomes theta, the velocity now becomes the angular speed omega, and the acceleration now becomes the angular acceleration alpha. And we also have equations that help us get between each one. Some of the helpful things from using the laws of physics is that the kinematic equations translate over very nicely from a particle under constant acceleration to a rigid object under constant angular acceleration. So again, angular acceleration for an object that we assume is even all the way around. So we were solving some of these problems yesterday and we finished with part C, I think, of the problem. So let me take us to part C. I'll remind you of the problem and then we'll continue there. So this is the problem we were solving yesterday. And in this problem, they gave us the constant speed, which was V. Notice the units and notice that it does not specify angular. So that's how we know it's velocity. And then they ask us to find the angular speed for each of these situations, for this radius and for this radius. So we can call one initial, maybe we can call this one initial, the inner track, and then this one final. And so here we very nicely solved for this problem, and we solved for the angular speed for 58 millimeters and the angular speed for 23 millimeters. And we also did that conversion to get us to revolutions per minute, which is, something more we can work with. And then the last problem that we finished was when the problem asks us to solve for revolutions, total revolutions during this time period. So of course we converted our time to seconds, and then we used one of the not so common kinematic equations, because we have these values here, and we use this to solve for that displacement. And so then we can say, what is the total amount of displacement with the unit of revolutions. And so that's what we solved for. And remember that this is just like radians. How many radians around did we go throughout the circle? And so this is the next question where we left off yesterday. So we have to remember everything that we kind of have here available to us. So the last question now is, what is the angular acceleration of the compact disk over this interval of time? And what's nice is that they give us this huge interval of time. So we know that this isn't an instantaneous angular acceleration. And we also solved for before the final and the initial angular speed. So this one will be a straightforward, change in angular speed over change of time. So here is how to solve for this one. So we're solving for angular acceleration and we have our delta time here. And so we just plug in the values that were given to us before. Um, yeah, that looks good. And notice here that it has an angular acceleration that is considered to be negative, right? So this angular acceleration could be that it's slowing down, or it could be that it's moving maybe a different direction. It really depends on the problem and what it is we're looking at here. Um, yeah, yeah, yeah. Really, I think what this negative means here um, is that it's slowing down, and I think that's something that we would expect, right? We expect a speed up of a CD, and then it finds its speed and it stays at some speed. But the initial speed up will be positive, and then once it needs to reach its actual rotation rate, right? It slows down to that rotation rate. So that's why we have the negative. But again, the negative could mean different things depending on the situation too. Okay, so everything we've done up to now, just like we did in kinematics, is describe motion. But we want to know, remember, like chapter 5 took us to the cause of motion. So kinematic equations will describe motion, but we want to know what is the cause of motion. And here, it is not going to be a grand surprise. It's going to be just like we did for the kinematic equations. We're going to pull from what we already know. So we know that the cause of a motion will be a force. Some sort of force is going to cause angular motion. And a good way to kind of determine how this angular motion changes from a force is to look at the scenario of a wrench. So this wrench is turning the bolt, right? So the wrench is going to cause that motion to change. The bolt is going to turn and it's centered around this axis here. Now, the wrench has a length where it has the magnitude R, that's our length here. And at this point, at the end of the wrench, we are gonna apply a force, okay? Now imagine when you are trying to loosen a bolt and you're applying a force. What will happen if you apply a force that is directly parallel to the wrench? What kind of action is this? Is this a like a pull?
The wrench comes off of the bolt.
Yeah, that I didn't even think of that. That's right. I would say the wrench will come off of the bolt, but what we're interested in is the motion. So here you're going to have no motion of the bolt because the wrench is going to come off, right? You're going to have no motion here. What if instead we pull up straight up on the wrench here, straight up? If you pull straight up, and a lot of times you've probably practiced this, when you're pulling straight up, that's almost the point where you're able to nudge it to get it to finally start moving. Now, what we're going to see is that if you pull on the wrench with any force in any direction, you will find that the vertical force is the force that's causing that motion versus this horizontal force. So if we speak from minimum to maximum force, you will get the maximum motion when you move in the most perpendicular direction to the wrench. So even if we were anywhere in between this, let's say this force here, some kind of diagonal force, the force that would cause the motion here is this vertical motion here. This horizontal motion or horizontal component of the force will cause no motion. How do we feel about this? Do we believe it? Do we agree? Do we, not believe it?
It kind of feels like the F should be the other direction, but I believe that it's right.
Oh, okay, so we see Keon says, I believe, Randy says, I believe, and yeah, it makes sense vertically. Okay, and Daniela agrees. So we have 3 people. So anytime you apply any force in any direction, whether the force is this direction or anywhere along this angle here, when you break down the components of that force, you will see that the only one that actually causes motion or rotation is this vertical one. So at the maximum angle, you must be perpendicular here. The reason this is a maximum angle is because of this angle theta. We can just call this theta, but it's phi on the screen. Anytime that you can maximize sine theta to equal 1, you will get the largest value of the force. Anytime you do anything that's less than sine theta equals 1, you will get a decimal and then only a percentage of that force. So if theta is 90 degrees, we will get, that's 90, right? Sine of 90 is equal to 1. Yeah, if we get sine of 90 equal to 1, then we will be able to maximize this force here. And so we call this then, in angular motion, we call this the torque. The angular motion, the angular force here that will cause a change in motion is torque. So this force here is a torque. And torque is a vector quantity, and it does measure the change in rotational motion of some object about some axis. And this is how we specify that this is rotational motion, that we are pivoting around this axis here at some length r. And so this ratio is very similar to what we saw in work, right? When we did work, we applied a force over some displacement, and then we were given the maximum horizontal value. But now we're applying a force across some displacement r, and now we're given the maximum vertical value. So instead of cosine, now we're going to have sine theta. So torque, the magnitude of the torque is defined as this RF sine theta, where this is the magnitude, the horizontal magnitude of the force that's being applied. And then you can shorten this definition for a maximum theta. For a maximum theta, then you'll just have RF, because sine theta could equal 1, right? And then here, another shortcut of writing this is by saying that D is equal to R sine theta. This isn't very common, but if you're to use the letter D here, it's just more common to speak in a situation that's always perpendicular. And if you're always perpendicular, then theta will always be 90 and sine of theta will always be 1. So it's also very common for max theta, you can just say that the torque's magnitude is equal to R times F. In fact, sometimes you'll see a perpendicular sign here, just to make it very obvious. That perpendicular sign just tells you that theta was 90 degrees. Let's see, what else do we want to add here? I think that's it. I think that's good. Okay, so just like in chapter 5, when we looked at the sum of the forces, the same will apply here, because this is what's causing the change in motion. So a sum of all of the forces will cause the total change in some direction. So we would write this just like we would when we write Newton's second law. And remember, when we write the sum of the forces, you're adding up all of the forces that are in the situation. So here we would write the sum of the torques are equal to actually adding up every torque that's present. And so in this blob, or your chicken nugget or your potato chip, or the elf ear, right? Again, you're centered around this axis here. And so this is just chosen to represent any scenario possible. It does, ocarina? What is somebody, I need to know. I don't know what that is. Ocarina? Someone tell me that. Oh, yeah. Thank you guys. Yeah. That's cool. So it could be, yes, it could be any elf ear. I never saw the elf ear. This is so funny. So I'll tell you though, the reason I chose a potato chip or a nugget is because I would always think about throwing something and it's spinning, right? Or a bean. Yes, Noah. or your pastor, your meat at the taco stand that's rotating. This is the same thing, right? You could have your meat here, and you could pick any piece of meat, some little quantity there, and center your axis there just to see what it's like, what the motion is like anywhere along this. So in this in this shape, the blob here, we are looking at an origin here, and with this origin here we can measure a distance, or r, a distance r, to the actual force. And here, F1, you see that there's a force being applied in this direction. Now, you guys tell me, if you have this shape here, right, and you have a force that's being applied in this direction, which way do you think this potato chip nugget is going to rotate? If force one is being applied kind of diagonally upward, do you think this will rotate this way, or do you think it's that force will cause it to rotate the other way? This one here is counterclockwise, and this one is clockwise. What do we think force one will it cause? Okay.
If they're both acting, it won't move, right?
Oh, okay. That's if they were completely symmetrical, yeah, you're right. If they were both acting on it, but you're going a few steps ahead. I think it's because you see that force one is some sort of slight counterclockwise that you guys are saying, and then I think what Randy is getting at is that then if we look at force two and we apply this force two here, you might think that this is going to cause a rotation moving clockwise. And so these two may balance each other out. And that's really good. Now we need to add some math to that. So anytime we see, this is our convention, that anytime we think that something is going to turn counterclockwise, we're going to consider that a positive torque. So anytime anything moves counterclockwise, it's going to be positive. And so the opposite is true. Anytime we see a force that causes a clockwise motion, we're going to call that a negative. And so now we can take the torques from up here, torque one and torque two, and we could say that force one is going to cause a counterclockwise motion, so it's going to be positive. And torque two here, this is going to cause torque two. We see a clockwise motion, and so torque two will be a negative, and that's why we have that negative there. And so then finally, the balancing out is coming up. And so we can say here that the sum of the torques, actually, I'll put it up here. The sum of the torques are equal to 0 if this were an equilibrium. If equilibrium, then this whole thing equals 0. And remember, equilibrium is very much like when a system is static and it's not moving. The word equilibrium means the same. Yeah, and Bafar is also agreeing with the counterclockwise. So here then, because our sum of our torques is equal to 0, we could just move one over to the other side and start solving for actual values here. So it would look like this, right? F1 D1 is equal to F2 D2. And this is really nice because you have 4 variables. So anything, if you're given 3 of them, you can solve for the other one. You can solve for the distance that torque 2 is being applied. You can solve for the force. You can solve for anything just by moving around the variables of the equation. And then let's say you have several torques, right? What if instead you also had a plus torque 3 here? And let's say torque 3 was this way, right? F3. Then this would be counterclockwise and it would be positive. So we could add in a positive F3 D3. And then that would be added in here too. This would be your entire equation. And you can also add in, I'm just going to add it in up here, plus F3 D3. So now you have several components of your equation. Several components of your equation. Just based on it being in equilibrium, you can start moving things around, which is really nice. Any questions about this so far? So what we've done is solve this in terms of the sum of all the torques that are being applied here. And this is giving us a magnitude. But what if instead they actually give us the vectors? Because torque is a vector. So if we're giving vectors, we can actually apply a new type of vector math here. And I think you guys have seen it. You mentioned it before. So what we can apply here now is the cross product. And they call it the vector. Oh, they call it the vector product here. So what we see then is that the torque here is going to equal the vector r crossed with the vector f. And so here it is. The vector r is the displacement from the origin to the particle. On the particle, let's say the end of the wrench, we apply some force in some direction, right? You apply some force here. And that is going to cause a motion with some magnitude, in the upward or downward direction. Oh my God. I'm just gonna draw in the wrench so you guys could kind of see that it's same old, same old. That's a wrench. It's a good wrench. So, so we have our wrench here and we're applying some force with your hand. I can't draw the hand. No, I don't think.
Okay, class.
No, I can't even picture it right now. If I had a moment, I could do it. But, you know, then you're, I don't know, there's like the wrist or something. The wrist. That's the best I can do.
Claw on a claw.
Yeah, let's draw a claw. There we go. So now your hand here is applying some force, right? You know, hands are famously hard to draw, but I think all it needs is time. All you need is some time. I love drawing or sketching, so I totally know what you're talking about with the hand, Keon. Okay, so yes, so here we have our hand applying a force, and what results is that the bolt here is either going to move upwards and have a positive torque, or it's going to move downwards in some negative direction here. And so this cross product brings us into a third dimension with some magnitude. It brings us into a new direction with some magnitude. And we know that that's going to depend on that vertical component of that force, if it's maximized. But if it's not maximized, right, we can use our vector products here too, our vector cross product here too. So now what is this cross product? The magnitude of this cross product here is, of course, that RF sine theta. And notice this is the magnitude of it. So we can say that the torque is defined as R cross F, and the magnitude of this is RF sine theta. That's that vertical. But we can actually do the math involved with this cross product here with any vectors. So we're going to take the torque out of the equation and just work with three vectors, any vectors, just like we did before. Let's say just A equals B cross C. It's probably the other way around. C equals B cross A, but that's fine. The point is that we can figure out what is this vector cross product. And so here it is. The cross product here, in this case, is C is equal to A cross B. So when we perform this cross product, we should end up with another vector. So that's the key here. The vector product is going to result in a vector. The dot product results in a scalar. So this means we need a magnitude and a direction here, right? So what we're actually doing is taking this A vector and crossing it with the B vector with some angle separated. And usually this theta is the smallest angle of theta. So you would not take, let's say, this angle of theta. You would only take the smallest angle. Now, physically and luckily, our right hand can help us with the directions here. So you're going to always naturally move your fingers in the way that they naturally move, which is turning in, or if your hand is outward like this, it'll turn inward. You're never going to move the other way. If you do move the other way, you have to put a negative in. But let's start with our right hand rule. So what's happening is you're going to point your fingers in the vector direction of A, and then you're going to sweep or cross to the direction of B. Once you do that, your thumb will naturally point in a direction. That is the direction of vector C. let's say you were to go the other way around, B cross A. So now B is going to sweep across A. B cross A here, B cross A, oh, it's down here, B cross A. For us to sweep in the natural direction, not backwards, we have to flip our hand down, and now these fingers become the vector B. B crosses into A, sweeps into A, and the thumb points naturally down. So notice, and so that gives us the negative C vector. So notice the first thing is that our fingers and our axis here that we're forming, right? Um, we can change these at any moment. You can say B sweeps into A, and then you have the vector C. They can move any direction you want, but what you want to keep consistent is the way that you cross them. So I like to think of the cross as the sweeping action, right? So B cross A, I'm gonna take my hands B, my fingers B, and sweep them into A, and my thumb naturally points downwards, and that'll give us that negative C.
Can you explain that again? Because when, like, if I think A sweep to B, that looks like it goes downward. B sweep to A looks like it goes upward.
So in each example, we flip what fingers represent the vectors. So let's go with the top one. Here, and hold your hand out. Everyone should be holding out their right hand out right now. And so the way your fingers point naturally straight out, right? I'm just pointing them out. This is your vector A. So vector A is then going to sweep, so you can turn your fingers in now pointing towards you, and that's the direction of vector B. Now when you push, when you stand your thumb up, your thumb will be pointed up, and that's the C. The other way to do this without the sweeping action is to use your two fingers here, and you can make your right hand rule gang sign, right? But notice that they're perpendicular, so they're on a different axis to each other. So you could say A crosses B, and B is pointing at me. A crosses B, and then point up to C. I hope that kind of makes sense. B is pointing back at me. And so then you can do the same thing for B cross A, but now B is being crossed into A. If B is being crossed, then B has to perform the sweeping action. So now these that were going to be the ones that were sweeping, right? For us to sweep B onto A, we have to flip it.
Okay, now I see.
Yeah, so B sweeping back into A, and A is always pointing out here, and then we flip back down. So your direction here absolutely matters. Just practicing this right hand rule will show you that. The magnitude of it all will always be that the two vectors times sine theta. This will always be the magnitude, but the direction will depend on the crossing action. And there's many ways to remember this, and I'll give you my shortcuts that I used in college as an undergrad, and it never goes away. You'll always see them too. But you can see that the direction really does matter of how you cross things in vector product, and it matters because the result is a vector, and the vector has a direction, whereas the scalar dot product did not have a direction. So let's come up with our major rules, and I think you'll see or get the hang of these really quickly. So for the first one, if we cross A cross B, if we take A cross B, the opposite order will result in the negative. So A cross B is the same as negative B cross A. Negative of B cross A. If we take the cross product of A cross B again, A and B, and the result is 0, then we know that A and B must be perpendicular to each other, must be parallel to each other. And this means that theta is equal to, what is it equal to? 0? Sine of 0 equals 0? Is that right?
Correct.
Y'all, thank you. I really don't remember these. I only remember them by the axis. So I have to think of them each time. So of course, if you try to cross a vector with itself, A cross A, the result will also be 0 because they're parallel to each other. And then we have the opposite. If A and B are perpendicular, then the magnitude of the cross product of A and B will be the magnitude of A times B, because again, sine theta here, or sine of 90, will equal 1, and it'll maximize that value. And so the order matters here, but you can still distribute the cross product. So if you want to take the cross product of the vector A and the sum of B plus C, you can distribute the cross product here and get A cross B plus A cross C. And then finally, the same with our derivative here. If you want to take the derivative of A cross C, you distribute, you take the derivative of the first and then cross it with the next vector. And then you add that to the opposite operation. I think this is like
Where does
the,
B come from?
it's what's the rule called? Like
Where
the
does B? It's there's no C in there.
this is just a typo.
Oh. It's like the product.
Product rule? Some of
Yeah, exactly.
Yeah, it's just like the product rule. Yeah. So this is really nice. You take the derivative of the first, cross it with the next, plus the first crossed with the derivative of the next. Now, the ones you really have to remember here are just these. The A cross B equals 0 when they're perpendicular. Actually, I'll box it so you know. You need to really know that one, and you should really know this one too. So you need to know the minimum and the maximum, right? If theta is equal to 90 and if theta is equal to 0. Anything in between, you'll probably have to use a calculator to get that sine theta value. Yeah, and so let me give you your shortcuts for the directions of vector directions when you're actually working with numbers. And again, you probably and may have seen this already, and please feel free to add to it. So our direction of our vector rules can very easily and nicely be written this way. First, you want to remember that counterclockwise is always positive and clockwise is always negative. And so if counterclockwise is positive, you can write the vectors I, J, K in this order and draw kind of a counterclockwise circle with a positive in between. And when you go follow the circle, I crossed with J, the direction will always result in a positive K. So I cross J will always result in a positive K. And this will be true all the way around. J cross K is positive I, K cross I is positive J. So we perform the multiplication of the number, the component, and then we attach the direction using the cross product. And then the opposite is true, right? For clockwise, the answer will always be negative. So you write again I, J, K in the order written here like a triangle. And now the circle moves clockwise and you have a negative sign in the middle. So J crossed with I will result in a negative K, or K crossed with J will result in a negative I. And you can do this again with your motion of your hands too. You know, if you cross I, cross J, you'll get K. So you'll see that motion with your hand. Another way to draw this circle out is here. You could see the same thing. Counterclockwise will always be positive and clockwise will always be negative. What I use is just this one, because just writing it once in positive, then I know the opposite is true. So I always write this somewhere just to keep it near me. This is a nice shortcut instead of memorizing this because this set of rules I think might throw you for a loop. I can't memorize this. I could certainly memorize the parallel ones, right? And I know I cross J will give me K, J crossed K in the right order will give me I, and K cross I will give me J, according to my circle here. But the ones in between, I have a lot of trouble remembering. So I suggest the circle. And then here's all the math. Let's say our last step, you know, you're given a vector, but you don't have any angles between them. And you know, let's say it's a simple vector, you could use the determinants. And that's the way you're taught, I think, in math to solve these. And so before you go through this, I'm gonna walk you through it, but let me remind you that whatever you learned and that method that works for you, keep that. I'm going to show you what the textbook did, and if you follow it, maybe you'll find it first. Um, Here's where they reverse things, but follow the method that you know. And so here's the cross product. We write it in a large determinant or a large matrix, and we write the directions at the top, I, J, K. Then you write the component of each vector for the I component for A, the J component for AY, and the K component for AZ. And the same for the next vector. And so then to solve for this, we do the determinant math for it. And I hope you guys have seen this. So for the first one, we would want to find what is the determinant for I. Yeah, okay, Luis. Luis is getting there. So it actually doesn't, and let me stop you guys before you all jump on this. This is correct. If you complete the math at home, you will see that they applied the negative. Yeah. So they just reversed the middle. I'm going to walk you through it just so you can see it. Yeah, that's right. They just switched the components, and that mathematically gives you that negative. So let's walk through it. So for the first one for I, right, your value will be the letter I here, the I hat, and you cross out the rest of the row and you cross out the rest of the column, and this becomes your determinant, AYBZ, AZBY. And here we know that we multiply across and then subtract it from the multiple across the other direction. And so then we would do the same thing for the next one. Many of you have learned it this way, so I'm gonna move it to the top. And this is also the way I would learn it. We learn that for every other determinant, there you start with a negative sign. And so then the next one here would be J hat, right? And so for J hat, I'm gonna take every step here. So bear with me, y'all. Let's just be patient while we're going through the math here. You circle this one, you cancel out the rest of the row, and you cancel out the column, and now you're left with AX, AZ, BX, and BZ. Okay, so that's probably the way many of you have learned it. That's also the way I learned it, and it's the way that I practice it. And then we would move on to the next one. The next one would be a positive. So we can focus on K hat now. Oy. Let's go pink. We focus on this K hat. You mark out the rest of the row and the column. And now here's your determinant, AX, AY, BX, BY. And again, we're going to multiply across and subtract it from the other diagonal product there. So when you sum all this up, this is what you should get. AY times BZ minus AZ times BY. Right? This is this cross product here minus this diagonal product here. Now, what do we get here, right? Notice what they did. They reversed the components here, and their result is AZ times BX minus AX times BZJ. Okay, let's see if it equals the same thing that we got here on this side. This is minus AX BZ minus, right? Minus, AZBX. Now I'm not looking, so I'm not actually, I know they should be true. So minus AXBZ minus AXBZ plus AZBX plus AZBX. So do whatever works for you. I like this one because when you go into linear algebra, you're going to work with matrices that are much larger than 3 by 3. And it's very convenient to remember that every other determinant is negative versus changing the components. But this is the way the textbook will show you how to use it. But I'm glad a few of you caught it right there. Yeah, that they switched the components. But I just wanted to show you that it is in fact correct. But it's just the way that you learn it. And then we're left with the final product, right? AXBY minus AYBX. and this is k hat. This is going to come back in Physics 102. In Physics 102, we'll have another cross product again, and you'll be reminded of this. So if has anyone not seen this in their math yet? I had one student. Oh, thank you. Okay, we got one. I had at least one student that didn't see this last year. Okay. Oh, we have a few también. Esmeralda, Andrea, and Matt. Okay, great. So you should practice this determinant form. I'll be very honest with you. I think the way we're going to do it will be not this way, but I'll show you the math way of just using just performing the math and then figuring out the direction using this circle here. So I suggest you go this route, but you will at least have seen it in this class. Oh, and someone else is telling it to me too. I haven't seen it in math yet, but I've seen it in MATLAB, so it was way easier. Yeah, you'll use this in MATLAB too. If anyone gets a chance to take MATLAB, I suggest it in the fall. Usually Dr. Navarro teaches it in the fall, and you'll see this in all your engineering classes too. Oh, okay, pre-calculus, you saw it too, great.
At City College, I took it at City.
Okay. And it was on the ACT. Oh, that's cool. I always, maybe next semester I'll ask in the beginning. I'm always curious who's in their like first semester in college versus like your second, third, fourth semester in college, because everyone has a different backgrounds here. So we're or 100th semester. That's true. So there's always there's always a refresher or a point where you can learn something new in class. So this is nice. And for those of you who have seen it, I'm very happy that you caught the way that the book reverses it. Yeah. or the very, very normal community college STEM major life is that you're a junior in credits, but you still have a few years left to go, which is very common for STEM majors at the community college level. But as long as you get there, that's what matters. Okay, so now we've seen a few ways to solve this. But ultimately it still comes down to this cross product. And so again, you can solve for the magnitude and say that's a magnitude, and say RF sine theta if you're given that information. If you're given the vector r and the vector f, you can just take this cross product and you can just perform the multiplication and add the direction in, or you can do the matrices, right? You can do either way. I suggest just doing the multiplication and add in the direction, but we'll see. And like many of you, they expect you to take 18 units in a semester to get it done in 2 years. Our goal is 100% to get you out in 2 years, but for you to be out in 2 years, you should be a full-time student that has pretty much nothing else going on in their life. And that is not everyone. It's not everyone at all. So
I have a friend that went to transferred to UCLA in the fall, and she for her all of her semesters at Trade Tech, she took more than 20 credits, and she worked a part-time job and another part-time job, and she got straight A's.
And that's the more common experience. If you're working, most community college students are working, or you have kids, or you're responsible for someone at home, or you're the head of your household and you have income and all kinds of things, right? So it's not easy to do it in 2 years. It's not, the point is to get it done,
You're a political science major though, so like.
Yeah, I gotta say, I'm one of those science people. I'm gonna just put it out there before everyone starts, bashing on other majors, that I very much value a liberal arts degree too. But do they have less units? Yes. Yes, they do.
It's crazy.
Yeah. I can't wait. I hope I'm really into your transfer curriculum, so I hope, again, I keep pushing everything to next week, but I'm really going to find a time next week for us to talk about it because, yeah, I can help you there. Um, okay, let us. Okay. Um, I just got to make this comment. I can't move on without saying it. But for anything that you transfer with, guys, just get your courses done. The most important thing is to get your science courses in. It's more important than the GPA. You need to have your courses done, your STEM courses done. You need to be as completed of a candidate as possible while working on that GPA, but you need to have as many courses as you can done. Because one way or another, that course has to get done, either here at the community college or at the university. Um, but the admission is based on how many courses you have completed within your major. So just, I gotta say it. Yeah. Yeah. Oh, show them that picture of classes engineers need. Yes, Keon. I'm thinking of all the things I could tell you guys, and I'm trying so hard not to so we can talk about physics, but maybe next week. How about maybe we do it next week after the exam? I think I can do the other, yeah, I think I can do the rest of the material on Tuesday and Wednesday and get it done. We'll see. We'll see. Okay, so let us practice this. It's not 50. It's like 30. Okay, let's practice the vector cross product now. And this is especially important for there. I think it's about half of you guys at least that haven't seen this in math. So let's actually try the examples. And this first example, we look at only working with vectors and not actually having any math involved, right? So let's try this one. Two vectors are in the XY plane and they're given by these equations, and notice that it's a vector notation. Find the cross product and then verify that the cross product will equal the negative of the cross product taken in the other order. So the cross product of A cross B, so the cross product of A and B is equal to the negative cross product of B and A. Notice we switched the order here. So let's take these vectors A and B to the other side and let's do the math one step at a time. So similar to the dot product, we're going to cross these two. So this is vector A crossed with vector B. And we're going to perform this just like you saw before, where you're going to distribute everything. The magnitudes will multiply, and then the directions are, you're going to perform the cross product. So this one written completely out is 2 cross negative I. The next one is 2I crossed with 2J. Oh, I think I left the other one off there. And then 3J crossed with negative I. And then finally 3J crossed with 2J. So here you can make some really quick things that you can cut out, right? Anything crossed with itself goes to 0. So this is 3 times 2, which is 6. But J cross J is equal to 0. So 6 times 0, this whole thing goes to 0. And so I crossed I will also go to 0. It'll be at -2, and this will also go to 0. So we're left with this. We would take, huh?
That one's positive and then the next one's negative.
Yeah, so we're gonna take I cross J. Ah, yeah, so Noah has a really good way of saying it. So in a second cross product, you can just FOIL. Yes, that's exactly what you're doing. I forget the math terms of these things, but let us see. Okay, so then this next one, 2 times 2 is 4, and I crossed with J, if we write our little circle, negative, right? No, positive.
Yeah. So we have inner positive, inner, negative, outer.
Yeah. So I cross J according to our circle here will equal K. So 4K hat, I hope that's right. I think that's right. And now let's do this one. 3 times, now you have two ways of doing this one. You can take the negative and count it as -1 and say 3 times -1 is -3, right? And now we do J cross I. J cross I should be a negative K. So you would take that times negative K. So this negative and this negative will get you that positive value. And so here's what you get. 4K plus 3K, because negative times negative make it positive. So we have to apply the negatives twice here. And so everything else goes to 0. And so the total answer now is, we can sum this up to 7K hat. So the value of A cross B is equal to 7K hat. Now we want to verify that the opposite is going to be negative 7K hat. Now we want to see, how do we get negative 7K hat? Right? So we take B cross A, and now you switch the order of the vectors. This was here, and now it's the first one, and you cross it with A, so B crossed with A, and you perform the same exact math. Negative I times 2I. Is this a typo? Yeah, this should be I. Yeah, this should be I. So you can distribute here, and some will go to 0 and some will flip. We'll flip the direction of K hat. And a question from Noah: you could also just make K equals 0 for each vector and do a third cross product to solve, right? I don't know. Make K equal, oh yeah, that's right. I see what you're saying, Noah. Like put in K equals 0. That's right. So here we do the same thing. I cross I will give us 0. J cross J will give us 0. And now you perform the direction here. This is negative 3, and times I cross J will give us positive K. So negative K hat, because of this negative here. And then this one is J cross I, which also gives us a negative K. So we end up with negative 3 and negative 4. And that'll give us negative 7K hat. So we found what the question asked us to verify, negative 7K hat. Question, comment? No?
Yeah, I'm just trying to understand your method for the J cross negative I hat.
Yeah.
How you do that with the wheel.
Yeah, okay, so this is the one that you're talking about. And yeah, let's do it with
it's positive. If it goes backwards, it's negative.
Yeah, so if we're following the arrows here, this is J cross I. Now you can do it two different ways here. You can, I'm gonna do it the way I would, like this negative I would be negative 1 I hat. So negative 1 times 3 is negative 3, J cross I. J crossed with I is going the opposite way of this positive, so it results in a negative K hat.
And what would you do if you had like a negative J minus I hat?
Okay, so that's a good question. This is the first way. Now let me do it the way of the directions. If I didn't assume that it was a negative 1 I hat, what if it actually was a negative I hat, right? So here you would have J cross negative I. J crossed with negative I should give us a K hat, but there's a negative I, so we need to put that negative times that negative K hat will then give us a positive. So that negative still carries through. I'm gonna do it one more time. J cross negative I. You can do this two ways. J cross with negative I in this order, J cross negative I will give us a positive K, but this was a negative, so we put a negative in front. Or you could say J cross negative I will flip it to the other direction and take us to K. So that negative still carries through. Either way, you either follow the circle and then add the negative, or the negative can flip the circle back the other way. You can do it many ways. And another comment, I'm kind of confused because I believe we learned that I cross I, J cross J, K cross K equals 1. Yeah, so this is very, very good. There's a huge difference between the dot product, which results in I dotted with I equals 1. This is the cross product, which results in I crossed with I equals 0. And this, let me give you guys another kind of intuitive thing that might help here, is that whenever you think of this dot product, did I just write DOJ. I think I did. This is the dot, yeah, dot product. This is looking at the horizontal component. So anything that is horizontally like parallel will result in a value. The cross product is looking at vertical components of forces. So anything that crosses with each other, that's vertical to each other, so perpendicular to each other, that will give you a large number. But anything that's in the same direction, because there's no vertical 90 degrees between them, that will give you a 0. So last week again was this dot product, and this week is the cross product. Do they both multiply through? Yes. So I could see where that confusion comes from. But the result is different in the direction. This one will be a scalar value, meaning that there is no direction. You're going to end up with a number. And this cross product is going to be a vector. So there is direction here. And because it's a vector and there is direction, it reminds me extra that like my XYZ gang sign here, this really matters. You have to cross from 2 planes to get into the 3rd plane. 2 planes will get you into the 3rd plane. Any way you move this around, 2 planes in between each finger will get you into the 3rd plane. Any way you move this, right, along, here's 1 plane, and this is moving straight into you guys. So the cross product will always result in that 3rd direction. Okay, there's another example here, and I promise we're about, if you're able to hang on, we're about 15 minutes away from a break. Yeah, I'll ask you guys in a second. Okay, let's try this one now with some math involved. I mean, some physics involved. So you have a force. This is F equals 2I hat plus 3J hat newtons, and it's applied to a rigid object that is pivoting around a fixed axis aligned to the Z coordinate axis. Okay. The force is applied at a point located at R equals 4I hat plus 5J hat meters. So R is in meters, relative to the axis. Find the torque applied to the object. So here, because we are given given the force and the displacement in vectors, you want to take that cross product. So this is the same as what we just did, C equals A cross B. Okay, so let's write this over on the other side and take the cross product and practice it. So it's, again, R cross F, and you're going to take the 2 vectors, vector R in meters and vector F, and you're going to cross them. Notice, again, we have our cross product here, not the dot product. And we're going to, I guess it's foiling, right? Distribute that multiplication. And you're basically looking at the scalar and then the direction, the magnitude and the direction of each one. So let's take this step by step. And again, if this is new to you, I would write every single step out for at least the first 2 problems. And then by the time we get to the exam and you've practiced, I think it should get a little more, you'll get the shortcuts. So we start here, 4 times 2, and then I hat crossed with I hat. This whole thing then is added and distributed with 4 times 3, and then I hat crossed with J hat. And that's what we have here. And we continue, 5J hat times 2I hat, and 5J hat times 3J hat. So these that are crossed with themselves, this is my finger I, crossed with another I, will never produce a 3rd direction. It's like pulling the wrench in the same direction. So this goes to 0, and J goes to 0. And with my fingers, it's like J in the Y. J crossed with J will never produce a 3rd direction in any way. And so these all go to 0 here. And so now we can take this product and do the circle, I, J, and I have very, very vivid memories of writing the circle while I was doing all of my homework for physics and math in undergrad and in my master's. I remember using it a lot. always writing this dumb little circle everywhere, but you need it. You need it. I wish I could tell you don't, but you totally do need it. Um, yeah, so just write it. Okay, so I cross J, we follow the circle. I cross J will give us a K. This will give us a K hat. And now this one, J cross I, yeah, yeah, oh, it'll give us a 2K hat. Where does it give us a 2? Okay.
I'm
Oh,
sorry. I'm
the
going
answer.
ahead. I'm sorry.
Yeah, no, it's okay. I'm glad we got the answer from someone already once. Okay, J cross I hat. So we go the opposite way, and that'll give us a negative K hat because I'm going opposite of my circle. J cross I gives us negative K hat. So this will give us a negative K hat. And let us confirm if we have 2K hat. Ah, we do. Okay, so 12 K hat is our first response, right? 4 times 3 K hat. And 5 times 2 times negative K hat, the negative comes to the front, minus 10 K hat. And so our answer is Newton meters. We're still multiplying the units through. And our torque then is 2K hat Newton meters. So think about what this physically means. You have a wrench and you have a bolt, right? I wish I had, at school, I have a giant wrench. I made a giant wrench because I think it's the coolest section. So you have this wrench here and you have a bolt, and your wrench here is the displacement that you see on the vectors there, 4I hat plus 5J hat. That's the direction it's in, and let's say it's, you know, some length. And with some force, 2I hat 3J, you're moving that bolt. You're moving the wrench, which causes the bolt to move, and the bolt's direction then will be a magnitude of 2 in the K hat direction. So upwards is loose, lefty loosey. Notice this is moving to the left. Well, left is counterclockwise. So this all physically should make sense. Clockwise is to the right, which is righty-tighty, which is negative. The bolt moves down. So think about how a bolt moves. A bolt moving down means you have to tighten or move to the right, which is clockwise. That's negative. Moving the bolt upward is the result of moving counterclockwise, which is positive. So this physically makes sense too, which is my favorite part of the torque, that it actually works with the wrench, right? Righty-tighty is clockwise negative, the bolt goes down and it tightens in. Okay, so we were correct, 2K hat, excellent. So are we okay? Can we go 4 more slides, or should we take a break? It's up to you guys. Oh, Keon, couldn't they thread the screws the opposite way? Let me tell you, yes. And the hardest, huh?
Some things are.
Yeah, some things are, but the hardest way of thinking about righty-tighty, lefty-loosey, imagine being like upside down, you know, and this is very common. I was doing this just the other day when I was trying to loosen a hex bolt. Like you need a hex key for it. And I'm thinking righty-tighty. I literally had to take my key, do righty-tighty the normally way, and then flip it so that I could turn it the right way, because yeah, the minute you change the axis, the rules are still the same, but you have to flip with it too. But if you want to, instead of threading the opposite way, just flip yourself upside down, Keon. do that. It'll work too. It'll be the same effect. And you never know, as a engineering grad student, many times I had to create the threading on some long rod. Many times I had to do that. So you don't want to go the opposite way, but you can. You could throw someone off. Okay, how are we doing? Can we go? I think I can do it in 10 minutes. Can we go 10 minutes? Okay, I got 1 thumbs up. I just want to make sure we're all okay. My legs are okay. I got a few more. Thank you, Gary, Saja, Andrea, Daniela. Thank you. Thanks, Randy. Okay, I see a bunch of you guys. Excellent. So let me go 10 more minutes. But oh, and Patricia, I see you too. But my legs are certainly feeling it. So we'll take a break soon. Okay, so now that we have this, what we've basically figured out is torque, and we looked at the sum of the torques. And so we related all of this to F, RF, right? So these are linear components, and this is all fine, but our goal the entire chapter is to find everything in angular components. So we can take everything we've learned from chapter 5 and this chapter and find our angular components for moving the torque, for torquing, for torquing something. Okay. Let's try it. So imagine again, you have your particle that's moving about some axis here, right? It's going to have a radial force that's pulling it inward, and it's also going to have this tangential force. So in our linear understanding, we would start with Newton's second law, right? Newton's second law is the sum of the forces equals ma. When we write Newton's second law like this, we're talking about the linear properties, just like we did in chapter 5. And now we're just distinguishing them with the t so that we know that they're tangential. But our goal is to then write them in angular. So the angular force that's involved here is the torque. So let us take then the sum of the torques are equal to this linear force that we're pushing the wrench with times that radius. We can take this definition here of this linear force and plug it in. So this then becomes the sum of the torque is equal to Fr, or MAT times R, where this is the tangential acceleration. But we know how to write the tangential acceleration in terms of angular components. Remember this, we know how to write this. I think it's A equals R alpha, right? I think we've seen this. So let's write that in now. Yeah, it is that. Okay, so now we write this in terms of R alpha, and here it is, MAT times R. This R just drops down. And now we can regroup this to look at, and we regroup it in terms of the particle. The particle has a certain mass and it has a certain location, and it is moving with the angular acceleration. So I group this in terms of the object. The object is described by the mass and its position. Then the angular component I leave on the outside. When we do this, we can now describe this term specific to the object, right? So this term specific to the object, we can now call it inertia. This here is our inertia, or it's our angular mass. It's kind of like our angular mass. And notice that this equation now, everything just comes down, and I will equal mr squared. Notice that this looks very similar to Newton's second law. So the sum of the torques equals inertia times the angular acceleration has the same form as Newton's second law for linear components. The sum of the forces equals mass times acceleration. So I'm gonna take this over to the other side. You're not gonna miss any of these equations. This is just a derivation. And so if you wanted to sum up all of the torques, the torque that's acting externally on a system, you would add up the individual components, torque 1, torque 2, torque 3, and each one of them has its own component, right? Mr squared alpha, and again, we group up the mr squared, and this is your inertia. So the sum of the torque is equal to the inertia times alpha, where the inertia is that individual component of the mass times the radius squared. And so, oh my gosh, I didn't want to flip over just yet. And so what you're really seeing here again is defining this angular mass. So this inertia here is the mass of all the particles, or the mass of the individual particle, with multiplied by its distance squared, right? Now look at the definition of what the inertia actually is. Oh my God, I can't even get my eraser out. The definition of the inertia is the same as the definition of mass in the linear world: the resistance to change in its rotational motion. So the only thing that's changed now is that we're looking at rotational motion. I think this is super cool. Like this is so entertaining to me. So this was mass before, right? This was mass. But now it's how does that mass resist change in rotational motion? And as soon as we do that, we're talking about the value of inertia. Um, and so here is then your summary that the torque, now written in all angular components, is the inertia times the angular acceleration. And so the way that we distinguish this is to its linear form. It's the sum of the external forces is equal to the total mass of a system times the acceleration that is centered on the mass, the center of mass. You don't need to know this. This is well, not for right now. We don't need to know this right now. But this is the proper way of writing Newton's second law if you go into advanced usually statics courses. So inertia plays the same role in rotational motion that mass plays in translational motion. We have an angular mass. So the last thing I'll say is that you might bring up the fact that, hey, masses have different shapes, right? You could have a sphere, right? That's a sphere. Oh God. Or you could have something that's like a cube. I'm not even gonna try. I'll go quick. Okay, I'm better at the cube apparently. But you can also have things that are like a rod or a cylinder, right? So there are many rules for this. In general, this will be the equation that we'll use for inertia when we're talking about any particle or any body. If you're given a specific shape though, there is a table of inertia or the moment of inertia for different shapes. So something like a hoop or a thin cylindrical shell, like a hoop, a hoop or a ring, you would use mr squared. For a solid cylinder, you would use 1/2 mr squared. So maybe something like a merry-go-round, right? Hollow cylinder, you have more. For a long rod that is centered around the middle of the rod, you would use 1/12 ml squared. But look at this one. For a long rod who is pivoting around the end of the rod, you would use 1/3 ml squared. So notice that these here are different. And also think about when you're spinning something, what's the easiest way to spin a rod? Like if you take your pencil, right, and you spin it on its vertical axis versus on its center axis versus on the tip of the lead. Think about that. I think it's pretty cool. You also have the moment of inertia of a sphere or a thin spherical shell, which is a hollowed out sphere. So anytime you would add that inertia times the angular acceleration, and you might have a few of them to add, this is the part that would change. You would just use this table. And the ones we use the most are this one, this one.
Isn't this what keeps like a bicycle upright, like when you're riding it?
Yeah. Yeah. The way it's down. Yeah, and you bring up a good point because when we think of torque and a wrench, you're usually spinning on like the plane with it. So the way that I'm pulling and pushing the wrench is this way. But you could apply torque in the opposite way. Imagine like a lever or a seesaw. You're applying torque in each direction. And I got 1 minute, so I'm just gonna show you really quick. Imagine a seesaw, and you have a person here, and then you have a really bigger person here, maybe an adult versus a child. The way that we would see this seesaw move, the adult would be much heavier, right? Force of gravity here. And so this would cause torque or rotation this way. And this turning motion here is considered counterclockwise. And so this here, they would move counterclockwise. If you change the mass around, then the torque action would be clockwise, right? So you don't have to think of it in just the plane. You can think of it upright, like a bicycle or a seesaw or a lever, or think of it with pliers too. I could go on and on, so I'm gonna stop. But this is where I wanna leave you guys today, with this and with this, the table of inertia. So these three are the ones we'll use the most. but the other ones are available to you too. Mathematically, they're all summed up the same way. Any comments or questions before we take a break? Anything? Okay, I see none. How about a break till 11:45? Is that too long, or 10 minutes instead, or 15? Okay. How about, yeah, when I hear okay, thank you guys. Yeah, when I hear no comments, I think we need more time. So 11:45, let's take it. I'll see you guys at 11:45. Thank you everyone who responded. 11:45. Hello. I hope some people are out there. I think I stopped sharing my screen. Hello. Hi, everyone. Hi, Robin, Keon, Saja, Owen. Hola. Buenos días. Is it still morning? Yeah, it is. Just barely. um, okay. Hi. Hi, Nate. Hi, Gary. Um, let me close off this PowerPoint and move us into our lab. And what's really nice is that this torque lab will take you into some situations where you can practice the math and see how quickly you can get an answer. But before we do that, let me take us through some practice first. We lost some people. Come back. Well, the good thing is that this next slide set will really help with the lab, and it's very helpful just to see the math that'll work and how we can apply this to like any situation. Okay, so I'm gonna share my screen and we're gonna do some torque. Okay, so this is what you should see now, and let me rearrange you guys. Let me get the chat out. Okay, so this next set of slides is kind of to help us with the math that we're going to need for the lab. Okay, so again, we're working with torque, and that's what you're going to measure in this lab too. And remember, this can be applied, can be applied to any situation where you're applying a force to an object that is pivoting about some center point, some axis. Hello. So here again, we don't have a wrench drawn out, but again, you're pivoting around this axis at some distance, and at that distance, you're applying a force. Notice in this situation that this force is perpendicular to the direction of the distance. So we're always going to get our maximum value here. So here you'll see it that the torque is equal to F times R. This is not the dot product. I'm going to put across. And you don't see the sine theta because this is at the maximum value, right? So this is theta equals 90. And this is a quick way to get to work with torque when the force is applied in a perpendicular way. In this case, we're using an applied force, and we're taking our hand and pushing it up. But you can always have another force of any type. Let's say instead of this applied force, you just had something. Maybe you decide to just sit, right? That's pretty good. So let's say you're sitting. The weight of your body would be the force. So this would be a force of gravity, right? And here, very nicely, we know that this equals mass times g, gravity. So you would just need your mass to figure out what's the force that's applying this torque here. So again, as long as they're perpendicular, you can just say F times R. The unit will be the Newton meter. That just comes from multiplying the force and the radius. And you want to remember that your sign convention is positive for counterclockwise and negative for clockwise. And if we need it, I'll remind us of this. So some situations where this works, remember that any way you vary the force and the radius will affect the torque. So some real life situations that you probably didn't know you were applying a torque, and you actually are. So here's some. For example, if you're using anything that has a long lever, a long handle, a long board of some sort, and you're applying a force in one direction, if it's centered about some axis, what you're doing is applying a torque. And some everyday examples of this are like the pliers. Those long pliers, what are those called? Like needle nose, okay. Those pliers are that long specifically so that you can apply less of a force. Imagine, or like the trebuchet, exactly. You have a specific radius here. If you have a very high radius and you apply a small force here, you're going to get some sort of torque. if on the other side, to balance that out, right, if this is balancing out, here you will have the result of a small radius, but you will get a large force exerted out that you didn't have to apply, right? So you see this in the catapult, in oars, when you're moving down a long river or lake of a large lake. That oar has a really small radius, right? A really small radius where you're holding it, and so you're having to push a large force there, and then the rest of the paddle, or the oar, I guess that's what it's called, has a long radius that's pushing with some force, or a crowbar, or even a seesaw, right? Or imagine, right? You guys have seen this when you're trying to get a car out of the ditch in a movie. You set this up like a long board of some sort on a rock, and then you jump on it here. This really long radius or long displacement that you have here with some small force will result in a very large force on the other side, large enough where you're able to move something that's much heavier than what you would be able to move with just your applied force. So this works very well. And then finally, in these situations, you're causing motion, right? But we also have the situations where you're in equilibrium. And when you're in equilibrium, the equations are really easy to manipulate because things equal to zero. So in equilibrium means that you're accelerating at zero. There is no acceleration here. So static equilibrium will equal that, a zero acceleration and a zero velocity, meaning that you're just balanced out. And this type of situation is something like this, where you're applying forces on each side equally. And this is, here the forces are being applied horizontally. So again, it could be any direction. So here, your total motion will be zero. But if you were to move over one of the forces, it'll cause an imbalance, and now you're going to cause a rotation, a motion. And if this rotates this direction with this arrow, this would be counterclockwise. So we would call that a positive torque. So this is in the vertical. Let's see it for something that we recognize. Okay, so here's an example problem, and you're going to have like one or two of these very similar to what you're going to use in the lab. So here you have a uniform board of 10 meters, and it's supported at the center. It's supported by something called a fulcrum, and this is what we would have done if we were in class, is use this support with a really sharp point here that you balance a meter stick on, but let's say a board. So if a person with 80 kilogram mass is standing 2 meters away from the center, how much force is required to balance the board at the other end? So remember, this whole thing is 10 meters, and this person with force 2 is applying a force downwards like this, and their mass is 80 kilograms, right? And they're standing 2 meters away. So this is 2 meters here. This whole thing, I think, then would be 5 meters. So we could sum up the torque that each thing is applying. Here's another applied force, force 1 on the other side. We can sum up these forces to figure out what is the force, the mysterious force on the other side. And then you can think of the directions of what direction is being applied here. If we look at only force 1 would cause this board, because it's centered here, it'll cause the board to move in this direction, right? This is called counterclockwise. If we were to look at just force 2, right, and force 2 is pushing downwards, it's going to cause the board to move that direction, right? And so this is called clockwise. And remember, if I actually am not good at remembering the clockwise one, so I have to do this. I have to go all the way around so that I could see the actual past 12 o'clock to see the clockwise. So whatever you got to do to help you out, yeah, this one's really easy because it starts at the top. Okay, so let's start by summing up the forces. Now remember, this is asking for the board to be balanced, which means equilibrium. So we can sum up our torques to equal 0. And then the sum of the torques would actually be, so this sum of the torques would be here. We would sum up all of the counterclockwise torques and all of the clockwise torques, which will be a negative. And this sum of all of the torques equals 0. Now we can move this one over to the other side because of the negative. And now you can sum up all of the counterclockwise torques to equal all of the clockwise torques. In this situation, we only have one force on each side. So all of the counterclockwise torques will sum up to just Fr. Remember that torque, no matter what, is F times R here. So force 1 times radius 1, and then this is equal to force 2 times R2. Now we know the mass here and the acceleration is gravity. Just remember that F here is equal to ma, and this is a here is the acceleration due to gravity, and radius 2 here is equal to 2 meters. Radius 1 here is equal to 5 meters because it's all the way on the outside, right? So how would we solve for this then? We would just move everything around and solve for F1. F1 equals F2 R2 R1. And that's how you can solve for this F1. And let me just write this so that we don't have any questions whatsoever. This is mass times gravity. So the mass here would be 80 kilograms. Gravity would be 9.8. And radius 2 would be 2 meters, and radius 1 would be 5 meters because it's supposed to be on the edge, right? All the way on the edge. So that's how you solve for force 1 here. Let's try an actual problem, and I think this one has numbers on it too. Let's try this one. A force of 5 newtons is applied downward 0.3 meters to the left of the fulcrum. Where would one exert a force of 1 newton downward to balance the stick? So the first thing is that it's asking where. Where means a position, R. And we actually don't know what side it's on, right? We can certainly make a guess that we can, huh?
Would you have to do 0.3 times 5 since it's 1
Yeah,
newton on the other side?
Yeah, let's write it out and see what this equation would look like, right? So here you would have the sum of the torques is equal to 0, and so this one would move. Okay, I see some answers already too, and I think Randy was telling us how to calculate it, right? So you would sum up your torques here. I think the other one has to be somewhere on this side, I think. So we can calculate it with that in mind. So torques counterclockwise minus the torque clockwise. I hope I got that right. I think so, because this one's always positive. So torques, I'm just going to take the long route to solve this problem, but you guys have already done this quickly. And so again, you have F times R is equal to, I'm going to say this is the unknown one because we don't know it. So I'll just call it X. And so here you would solve for this Rx. What position would it be at, right? So F times R over Fx. And then you guys were giving me some values already. F times R, Randy, you were telling us 5 times 0.3, right?
Yeah.
Okay, 5 times 0.3, and then F of X here would be 1 Newton. So 1 Newton, perfect. Okay, so then if we solve for it, you guys told me the answer already. Is it 2? Oh, it's 1.5 meters to the right. Did we get that? Oh, okay. Yeah. So the answer here would come out to be a positive value, and what that positive tells us is that the assumption that we made that it was clockwise is correct. If we assumed that it was clockwise, which already implies a negative, and this answer came out to be negative, that means we'd have to flip it and write it on the other direction, the other side. So yeah, 5 times 0.3 is 1.5 meters divided by 1. The units cancel out, the newtons cancel out, and we get our radius. Okay, so you guys have a good idea of doing this. Actually, dang it, I didn't realize I had it already done it all. My bad. I forget sometimes that I spent time actually writing this stuff out. Well, there it is. There it is. My bad. This is a nicer screenshot than what I wrote. So, okay. So let me see. Let's see if I think I have one more for you guys. Oh yeah. So that's where it ends up being. It ends up being 1.5 meters over here. And that's our correct answer there. Do we have another one? Oh, we do. Is that the same one? No, it's not the same. Okay, let's try this one. This is going to flip it on you. We still have a 5 Newton downward force at 0.3 meters to the left, and we still have our 1 Newton that we now know is 1.5 meters to the right. Okay, how much force is applied by the fulcrum to the bar? So the bar is in equilibrium. The fulcrum is applying a force upward. The force of the fulcrum is being applied upward. What is the force downward that's balancing the board here to stay in place? Any guesses out there?
Is it 6 newtons?
Okay, I hear 6 newtons. I see 6 newtons from Nathan and from Randy. And yeah, so this one would be 6 newtons, and you would do the same thing you did, but now instead of applying the forces to angular motion using the torques, we go back to our vertical forces, right? So the sum of the forces in y will equal 0 because in y nothing is moving. And now we sum up all of the forces that are being applied. The -5 pointing down, the -1 pointing down, plus the unknown force of the fulcrum pointing upwards. So we move everything around and this upward force is 6 newtons. Really nice, huh? So what your lab is going to be is this type. This is what we actually would have done at Trade Tech. We have a fulcrum and you would balance a meter stick and you would all take like, believe it or not, you would take like 15 minutes or so to try to balance out that meter stick and you'd all get upset with me. That happens every semester. But in this one, we can just assume that it's in the middle. The meter stick is balanced. What happens in real life is that the meter sticks are, they're worn down. So the mass isn't actually equal on both sides. So you have to find your new center. So sometimes it's a little bit over to one side, depending on how how the meter stick's been treated. I see other people had the answer too, Daniela and Esmeralda. Very good. Okay, so what we just did was a model of this, right? We have a certain distance of, let's say if you're using a meter stick, you have lines here that you can use as the center. And then you can hang masses on either end or sit the masses up top on either end and then figure out how to balance it out. Now, additionally, you could take this a step further and put several masses on one side and still balance out the equation. Both of these would be the clockwise, right? These would be the torques clockwise, both of these. And this would be the torque then counterclockwise. So in this case, when you were to balance these out, you would sum up two forces on this side. You would have the force, what is it? F equals ma, so mg times r, fr of 2 plus f3r3. And then on this side,
The FR, what is that again?
fr is the torque.
The torque, oh, okay.
But I think what you're probably thinking is what is the force? And the force is, if it's hanging, it's the mass due to mass and the acceleration due to gravity. So as long as you know the mass, you can figure out what is the force that's being applied with gravity. So again, this is the equation you're solving for, right? And you can solve for any variable that you want. Additionally, you could solve for some unknown mass. What if you know the distance, the center point of where it's going to sit, but you don't know what the mass is? You can just solve that in the equation that you just saw on the other side, right? You could solve for this unknown mass in either way. You just set it up. The other thing we could solve for is what if you're given a known mass, but you don't know where it goes? What if now you have this equation and you don't know if the mass is going to be, which side it's going to be on? You just assign it to some side and then see if the answer comes out positive or negative, and you'll get a distance of where it's going to be. So that's what we're going to do in today's lab. Any questions so far about this? This is going to be helpful to you guys, this equation here. For this example, here. Okay, so if you already looked at the lab, then this might make sense to you all now. But if not, let me take you to it.
Professor, could I just ask you to see that last slide again? Because it looked like the R's were all 3's in that equation that you said was important.
I hope not. Let me see. Oh, I erased it. Oh, but they should not be all 3's.
You want it to be like F1 R1 equals F2 R2 plus F3 R3, right?
Yes, yes. If anyone watches the recording and I wrote R3 all the way around, that is incorrect. The radius belongs to the force. So yes, F1 R1 equals F2 R2 plus F3 R3. Okay, let me take us to the lab. Let me find it. Ah. I'm almost there, I swear. Give me a second. Oh, I should say that I'm about halfway through, more than halfway through exam 2. But again, the internet really messed me up again last night. But I'm gonna just keep trying. I'm pretty sure I will still finish before Thursday. So we try. Okay, let me open up the lab. Go into student mode.
Thursday is that drop day, right?
I think it's Thursday. The 30th? Yeah. Yeah, I think it's Thursday. I'll double check and remind you guys, but I'm pretty sure it's Thursday. Okay. Okay, let me share my screen. And let us go to the lab. I can't tell you guys enough how much I love this section. I love the torque section and I love the lab section. Okay, let me open my chat window. Oh, the 30th is Saturday. Thank you, Saja. Yeah. So, oh, it's Saturday. Oh, good. I'm still going to try to finish by Thursday. I'm going to try because I have more things to do and it's just going to keep piling on. Okay, so let's go to the lab balancing act. Okay, so first, always read the description, right? So submit by Friday. We're back on our Friday schedule. Use the simulation below, explore its features, complete the game in Balancing Act Level 4. All right. As you work through the challenges, solve the equilibrium problems separately for submission. So you will mathematically solve each situation. I think it's about 6. You will solve each one and you will show all your work, including equations, units, and solutions to each scenario in the game until you get to level 4. Oh, it is 6. Attach a screenshot of the final screen once the game ends that shows your score for the 6 challenges. If you end up showing me the screenshot for everything, that's fine, but the easiest one is the last one with your score on it. You're not graded on the score. You're graded that you finish it, but you want to show your work. Okay, submit your work for each challenge and the screenshot as a PDF. And of course, you can submit late. So here it is. Before you guys ask, do you need to write a discussion or a conclusion or an introduction? No, because it does not say it here. I mean, unless you want to, but I won't read it. Yeah, it's okay. It's okay. I know. I see. Kian said that was hard. Oh boy. Okay, so let us work through it. What's the first instruction? What am I supposed to do? Okay, complete balancing act level 4. Okay, let us go through the introduction because you know that's what you're supposed to do, right? Um, I'm gonna go big screen instead. Okay, so introduction, just so you can see everything. We have something that looks like a fulcrum, a balanced out board, and you have tick marks, but look at everything we have available to us. You can show mass labels, which means 5 kilogram, 5 kilogram, 10 kilograms, forces from the objects. Once we place the object down, for example, you place the object down and you see an arrow with the force pointing down. So this will give you a clue that it's clockwise. And the level here is this level here. You see the level that it's in equilibrium right now. The position, you have none right now. You can use a ruler and now you have what looks like a meter stick, or you can use tick marks. These are just numbers, right? So you can also use the 1 tick, 2 tick, 3 tick. You can use anything. The ruler is nice because it's in meters. And here you have it balanced out. So if you click the other way, you've taken off the little pillars that were holding it off and now it's unbalanced. So your goal is to kind of go through the different challenges that will be presented and try to keep this balanced out. So if we place 5 kilograms here, you know, it's really easy to guess that to balance it out, the other side will be equivalent there. But what if, anyone here take a guess? What if I put this at 5 kilograms here? Any guesses? Oh, bless you.
Sorry. Thank you.
Any guesses where this might go?
Oh, I did this lab last semester.
Yeah. Yes.
It would go, that's 10, put it at 1.25 negative.
Ah, it turned green. It's balanced, right? So this was good. Randy, was that a quick guess or did you remember or did you do it mathematically really quick?
I remember doing this lab and I remember how, but I don't remember the exact numbers, obviously, I guess.
Yeah, so this one, a quick way is that, of course, halfway through 1 and 1.5 is 1.25. So this is the intro part. Now we go to our balance lab and you can actually do things, but go to the game, okay? Go to the game and complete level 4. Click on game, complete level 4, and good luck, my friends. I'm gonna go through 1 or 2 with you guys, and anyone out there, give me some guesses because I'm not gonna put it anywhere until you tell me to. So here is what we're trying to do. So what's going to happen here? This is the question, what will happen if you remove the pillars? Is it going to balance to the left or move to the left, be balanced, or move to the right? Any guesses out there? You have a 40 kilogram here. I'm gonna put the ruler on. 40 kilogram here, 4 kilogram at 1, and 5 kilograms at 1.5. Very mismatched. What do we think? Okay, I see one response that it's going to move to the left, another to the left, definitely to the left. Okay, so we have 2 to the left and a very strong to the left. So let's click on the left. Let's check it. Owen. Owen. Yeah, everyone is shocked. Let us try again. So I think I see some new answers to the right. Owen got played. Daniela is shocked. Owen says still to the left. Owen, my friend. Or Isla says center. Let's go right first and then we'll go center. It did in fact move to the right. So we got plus 1 point to our thing here, right? So then you go to the next level and now you want to balance me. This is not a rigged carnival game. Our code is not broken. This is physics. So look at what you have now. You have this, what are these called? Cinder blocks, right? Something like that. The cement thingies. 1.25 distance at 12 kilograms, 20 kilograms at 0.25, and this person weighs 80 kilograms. Any quick guesses out there? Yes, a cinder block. Any guesses out there? Where should I put it? The goal is to balance it. So if you can quickly do the equation, you can just try it and you'll get your score on there, your full points. That's what the lab is, for you to write it all out. How to solve this. Any guesses out there?
0.25 meters.
Okay, thank you, Kian. We have a 0.25 meters. Owen says 0.5. We'll try that one next. So here he is sitting at 0.25. Okay. Oh, Patricia says 0.5 also. Ah, it was right. Kian, did you guess that or did you calculate quickly? Or
I calculated it.
okay, yeah. So it's pretty quick, and all you gotta do is the math for it. Owen, we gotta use some math. Okay, and so you guys will see the next game then. What is the mass here? So you don't know what the mass is of this television, so you need to put this somewhere to balance this out. And then once it's balanced out, you can solve the equation. So I'll let you figure out where this should be balanced, and then you can solve the math and figure out what the mass should be. I don't know. Uh-oh. Uh-oh. I think I've done too much. Okay, I'll let y'all do the rest, but I'm curious. I was wrong anyways. Okay, but at least you now know where to balance this out. So you want to get to the final screen, and it'll clearly show you that you've gotten to the last one, that you finished, and it'll give you a grand score. And you want to take that screenshot and show 6 different sets of work for each problem, and take the time to figure this out yourself. You certainly are going to see torque type problems like this on the exam, so take the time to figure it out. Okay, any questions about the lab? Any questions at all? Okay, I'm going to stop sharing my screen. I'm also going to stop recording, and I will stay on if anyone has any questions for me. I'll stick around, but you guys are free to go. This is, yes, Owen, this is a wonderful chapter. Bye, Mehmet. I'm going to stop recording.
Thank you, Professor.
Thanks, Kian. Bye.
Good afternoon.
You too. Thank you.